Really great to see you all here participating in our webinar. And today we are recording this event, and the recording will be available after the event. So you can find that at our websites, and we will provide the details later. And this webinar is organized by two centers in Finland. So we have the Finnish Center for AI, FCAI, that's spearheading our AI research in Finland and aiming for real-life impact of AI. And then this is organized also by HiDATA, so Helsinki Centre for Data Science, that is supporting our data science community. And we have excellent synergies with these two centers. And today we discuss, and in our webinar series, we discuss how AI and data science can help in understanding and also mitigating COVID-19 and its effects. And today we have really an excellent program coming up with two talks around the possibilities that science and technology offers. So this event is now today hosted by myself. So I'm Sasu Tarkoma, Professor of Computer Science at the University of Helsinki, and also the head of the Computer Science Department. And I also lead the HiDATA Center as well. And the program for today, so as mentioned, so we have two excellent talks coming up. So we have first Oguzhan Gencoglu telling us about computer vision for crowd analysis. So this is of course a very important topic, how to understand the density, people density of places, for example, very important measure for mitigating the spread of disease. And then we have the second talk for today given by Indre Zliobaite, and the talk is titled Words in Translation, Lessons Learned from Concept-Driven Research. And Indre is a pioneer in the research of concept drift. And each of the talks is about 20 minutes, and then we have 10 minutes for questions and answers. And we hope that we will get many questions and a lot of interaction during the event. And you can write your questions and comments in the chat, and we will then cover those. Or you can then raise your hand. So we have the hand icon, and then you will get your turn in kind of presenting the question and the feedback. And if you write in the chat, so we will then also ask you to kind of present this as well. So that's the plan for the questions and answers. And now we can continue with the talks. So first, as mentioned, so we have Oguzhan Gencoglu telling us about computer vision for crowd analysis. And he is co-founder and head of AI at Top Data Science, which is a Helsinki-based AI startup that provides AI development as a service. And he has extensive background in machine learning, so he has conducted research in many places, many countries, including US and of course Europe. And now he's participating and leading this Helsinki-based startup. And now let's give the floor to him. So please.
Hello, everybody. Thank you, Sasu. First of all, thank you for your time, everybody. Thanks for participating. My name is Oguzhan Gencoglu. Today I'll be talking about computer vision for crowd analysis and in the context of COVID-19. I am head of AI at Top Data Science. As mentioned, Top Data Science is a AI as a service company located in Helsinki. Shortly, we have delivered more than 70 machine learning solutions in various industries. So we are good at solving problems with machine learning, and our clients are good at, well, having problems. So it's been a good match, and I'm leading the AI team. All right. So let's start with the problem statement. Pandemic is such an adverse global health event that it's slightly different from other adverse events because the primary responsibility of risk management in pandemic is not centralized to a single institution, but distributed across society. So risk management is actually uh, taking care of us individuals, by complying to certain preventive measures such as social distancing or wearing a mask or staying inside, etc. So this is different from maybe other adverse events such as a earthquake maybe, which an individual has much less risk management capabilities, but the government and relevant institution has to do that. On the other hand, pandemic is very much related to how we as individuals understand this responsibility and behave in such a manner that this thing will be solved, hopefully. And adequate monitoring of crowds and the behavior of crowds in public basically emerged as an immediate need. This is not a new research problem, but now this is very relevant, obviously due to recent events. So if we can develop uh, scalable solutions such as computer vision and AI to properly monitor crowds, their behavior, then we can create actually timely interventions to prevent adverse things. For example, we can detect certain places in a shopping mall or in public that are especially crowded. We can announce certain announcements if there's certain amounts of people exceeds the limit. We can put some hand sanitizers there. We can put some signs on the walls in those specific places. So this becomes very relevant. Crowd counting and crowd analysis becomes very relevant in today's times. All right, so I was talking about crowd counting, and the opportunities related to context of COVID-19 include understanding crowd behavior, making timely interventions, preventing basically breaking rules of certain social distancing measures, and understanding crowd flow. And the challenges were technical, privacy, and business challenges. Uh, so I will elaborate a bit more on that. So from the technical dive, uh, the first thing that many companies or many research publications propose is employing a person detector, an object detector. Um, this is kind of well studied, especially from the autonomous driving perspective, because you need to detect pedestrians inside systems. And the problem with such object detectors is that when the scene gets crowded and when the camera is in such a view that the objects are overlapping with each other, so there's lots of obstruction, and the objects in this context, the humans, are small, object detectors fail. Second proposed approach is employing a face detector. So many publications they argument that okay, the whole body of people are not visible because they are on top of each other in a crowd, but the the faces are visible. And face detection is rather well studied, but this fails to work in aerial views when the camera is from the top, and also most importantly, this violates privacy. So face detection is a controversial topic, and we would like to avoid such systems if possible. Uh, Another approach is formulating the problem as a regression problem. Regression means that trying to infer the total count of the crowd directly from the image as a single number. So an input is an image, and the machine learning algorithm, in most cases, it's a convolutional neural net model, uh, infers the total amount of people in an image. So this works better than object detection methods because it doesn't care about too much about if objects are overlapping. But it fails to work if the scene has more people than the training data or less people than the training data. So it has a generalization problem. And our approach that we have formulated is that we reformulate the problem as an image-to-image learning one. So we infer the crowd probability heat maps from an input image and calculate the crowd amount from that density function. So this works better than object detection methods, and it can generalize to unseen number of people in a scene. So it can generalize to new data that it hasn't seen in the training set. And the privacy is preserved because we don't try to detect faces. We don't even try to detect people as objects. An example on the left is a camera is rather far away. There's a huge amount of crowd, and on the right, the camera is rather close by. It's street view. There are maybe about 20 people, and the objects are bigger. So our algorithm can capture and generalize to both of these situations because we try to predict a probability heat map. So it's in the number of people perspective, it's a scalable approach. An example result of our solution: a faraway view, a probability density heat map, a close by view with less people, we still can capture the probability density. There are certain tricks and bells and whistles to make this work. Obviously, we are using a convolutional neural net. That's pretty much the state of the art. But to give the perspective or the depth info, certain perspective transformation help the accuracy, increase the performance of the algorithm. This is one trick we have been employing during training. Then another trick, maybe a bit technical, but we actually have such an architecture that the convolutional strides are varying, and we do some channel-wise averaging to be able to generalize both this kind of small objects and large objects and close views and faraway views. Couple of bells and whistles. And example results of our algorithm include as such. In this image, the crowd is predicted as 1,500. Another image, I would like to remind that we don't detect faces as such. So it's probability density heat maps overlap with the original image. And even a video, I can show how our algorithm is working. So we can infer the crowd count simply from the probability of the crowd in each frame. So I would like to talk about maybe a bit scalability from a business perspective. So as a company, we are scientific people and we are R&D driven, but we are a company, we are a business, and we would like to go all the way to production. So this is one of our differentiators, maybe compared to other startups or other companies, other data science teams. Many people do AI proof of concept one after another, but very few make these AI solutions into production level solutions. And from 70 plus projects we have delivered, my observation is that basically many teams approach a given problem as such. Okay, let's run a proof of concept project. Then we will see if it's working. We will run a pilot. Then let's see if it's working. We will scale it up, productionize it. I strongly advise against this point of view or this approach. Obviously, we follow the proof of concept, pilot, productionization pipeline, but the whole is greater than the sum of its parts. So as a team, we always have the production in mind already at the proof of concept stage. So that's why, for example, this crowd count solution we have developed is already in production in Japan. Actually, Japanese real estate development company securing actually reopened their event venues with our crowd counting algorithm, because already from the proof of concept phase, we have been in close contact with the actual problem owners and developing the solution already from the beginning, having the production in mind. A couple of additions we have been working on. I have a couple of slides left, bear with me. So obviously this solution can count the crowd, but we would also like to have the exact amount of distance between people. And this is possible in a stereo view. Actually, this is a well-studied problem in computer vision. If you have stereo, means when you have several cameras, 2 or more cameras, it's basically geometry problem, right? So you can estimate the depth of if you have several cameras, and if you calibrate, if you have these distances. This is a well-studied problem, especially in autonomous driving. But calibration is expensive. Well, cameras are expensive. So can we solve this stereo depth estimation with a single camera? It turned out that with recent research, you can do pretty good. For example, this is one of our approaches that estimating the depth. So on the left, you can see the bird eye view from the top view, which has the depth of each object from a single camera. So just from this is from Helsinki, just from the context as well as the movement and the object sizes, the depth, the distance can be inferred actually, and we are incorporating such algorithms to our crowd counting algorithm to infer the exact real distance in the world actually. That was my talk. My name is Oguzhan Gencoglu. I would be happy to hear your questions and comments and answer them as much as I can. Thank you.
Thank you very much for the talk. And now we can have some questions. So, who is the first one? We have also the chat here, so you can write your questions as well. So perhaps I start. So I will ask about privacy. So of course,
Yes.
You have the video cameras and you're recording people. So there are concerns about privacy. So how are you approaching this?
Yeah, so basically, we are not the end solution provider in that sense. So this is something we really co-create with the client. In this case, it might be a security camera system provider, or maybe a shopping mall, or actually a governmental institution. So we do our best to explain how the solution works, and in a totally transparent way, showing the results, showing the algorithms as white box as possible, and showing that we are not detecting people. So basically, this is nothing other than having security cameras, which we already have, because we are not detecting neither people as objects nor face detection. But obviously, the people who are in a shopping mall, well, when we go there, there's a sign that there are security cameras, or you might be under surveillance, not in an identification manner, but for the purpose of, let's say, public health.
Okay, thank you. So maybe as a follow-up, so have you considered edge computing here so that you would localize the computing?
Yes, that's something actually we have been discussing, and it's actually needed. So we have quite some experience in that kind of let's say, edge inference, both from the machine learning perspective, meaning that having maybe a bit more humble machine learning models, or pruning the models, quantizing models to have smaller versions of it with very little, let's say, trade-off from detection performance. And this is something in our talks right now, actually, with our clients, that a local server should be able to run these, or maybe even on the camera in embedded devices. On the camera, it's possible to run these models. Yes.
Okay, thank you. And now we have one question from the chat. So very nice talk. How have you built your data set? Is it open source or do you have an inbuilt image data set?
Hybrid, I would say. So there are a couple of open source data sets available also for commercial use. Then if you have certain scenes and certain circumstances that data sets can't capture statistically, we can annotate or have some third parties to annotate a bit more data. This annotation is surprisingly fast because we don't try to pixel-wise segment things. We don't try to even bounding box. It's more like putting certain dots. But we don't do much annotation ourselves. It's mostly using what's available to everyone in the world.
Okay, thank you. So we have also another question. So perhaps I will read this
Sure.
as well. So it's about privacy preserved machine learning. And the question is that is it possible to overcome the bias in auto hiring? So I guess this now relates to kind of also other cases than counting people, but the question is really about bias. So how do you address this?
Yeah, so there have been certain news that especially large companies actually started to employ computer vision solutions for autonomous hiring of people. In my opinion, this is a great way to automate the bias that humans already have. So I think we should be very careful in this. But going into technical perspective, privacy preserving AI basically can be federated learning kind of solutions, or basically blocking certain features to the algorithm so that the algorithm cannot infer such, let's say, privacy important attributes. On the other hand, it's an open question that even though an attribute may not be there due to correlations, some other attribute may carry that information, that sensitive information. So there's quite some research on this topic, especially in NLP, natural language processing. It's well known that actually as the machine learning model gets stronger, it reinforces our social biases even more. I believe talking about things will actually help that people would be aware, more conscious, and we all will be conscious about these technologies. But thank you for the question.
Thank you. And then we have also one additional question. So this is about the architecture that you have used for detection. So how much are you using these well-known image detection architectures and libraries, like we have ResNet and these others? So how much is kind of built on state-of-the-art, and how much is your own in-house contribution?
Typically, we start a benchmark with, let's say, ResNet or these well-known architectures, and then depending on the client preferences and requirements, meaning the speed, accuracy trade-offs, etc., we do some, let's say, custom-made solutions and architectures. Nowadays, there are also certain automated machine learning solutions, especially neural architecture search solutions, that can automatically find actually better architectures suiting your problem. But I don't think they are as ready as plug and play stuff. So typically, we wrote a paper on this actually. It turns out that given the same computation power, neural architecture search is pretty much as good as random search. We don't employ such solutions, but we start with the baseline and do a bit of bells and whistles, change the architecture to fit to each tailored problem.
Indre Zliobaite's presentation, so Worlds in Transition, lessons learned from concept-driven research. And Indre is tenure-track professor at the Department of Computer Science at the University of Helsinki, and she leads a research group of data science and evolution, and has made pioneering contributions to this field. So Indre, please go ahead.
Thank you. And here I am. So I'll switch the camera off for the presentation. Yes, interesting times. Share screen. Yes. Yes. Can you see my slides?
Yes, we do.
Yeah. Okay. So yeah, interesting times we are living in today. Not many of us, at least I don't know much more about COVID-19 than we see in the media, but interesting parallels come up with ongoing research in machine learning on concept drift that has been now perhaps nearly 20 years old. So I'll give you a flash introduction into this research field. And then I will speculate a little bit what it means and what challenges it brings in or can potentially solve in the context of COVID-19. I'm an academic professor nowadays, but I also have 7 years experience in industry, in banking, in credit scoring. So I'll be making quite a few examples also from the banking perspective. Right. So machine learning for evolving data and concept drift. So when we make predictive models, anywhere for decision support, for monitoring things or traffic or control of production, for predicting interests of consumers or credit scoring, or anywhere in our society where predictive models are used, we usually assume that the world as is today will remain so for the foreseeable future. So concept drift research is how to adapt predictive models, how to make predictive models to diagnose themselves and adapt when the world is changing. And an example you see here in the lower part of the slide is from a chemical production process, sensory data. This is a project I was involved now nearly maybe 8 years ago. So in chemical production, so on the left you see a chemical production plant, huge one. There are sensors monitoring the process. And here in particular, the goal is to predict the quality of the production that's coming out at the end of the pipe. And of course, it cannot be done manually because it's too laborious and it takes too much time, and it cannot be done online. So predictive models are used to monitor production process. And what you see in the graph, the black is called soft sensor. So that's the predictive model over time, predicting the quality of the output. And then the red one is the true value of what is being measured. Let's not go into details how it is measured for the time being, but suppose that we know here the ground truth. And so we see that at around this point, something happens and the predictive model goes out of tune. So there's a shift. And we see that the finer nuances are still captured. So when it goes up in the model as well. So the model does not become obsolete completely, but there is something wrong. And a nice thing to do would be to monitor for these things to happen and to automatically put the models back on track rather than discarding and redoing them from scratch. And this is just an illustration, but this can happen in many different situations, shifting user interests, traffic jams due to different road construction or different habits of people in many different areas. And the primary reason for this to happen is that when we do predictive models, we usually at the large scale, at the global scale or country scale, or even a company scale, we do them in an associative way, not in a, our models are usually not causal. Making a causal predictive model is very difficult in a data-driven way and usually infeasible unless we can model the world as a whole. So when models are associative, so many things can happen. The environment can change, users or like the agents themselves can change their preferences. Adversaries can act, like in intrusion detection or any fraud detection. So adversaries would deliberately try to change, to break the sort of the patterns that the model has learned. Or the prediction task can be so complex that we just cannot take everything into account and we take one part at a time. For example, if one makes models for, say, controlling self-driving cars, make a model for a city, shift the car to a desert, and perhaps some of the relationships will not hold anymore. So that's the context for concept drift. So concept drift happens when something in the context or in the unobserved variables or unmeasurable variables change, and and that breaks the patterns that model has learned to make its predictions. So going to COVID-19, here I took some examples from Google Trends. That's the keywords that people are searching, how their intensity is changing over time. So this can show us how user interests or user preferences are changing over time in the context of COVID-19, which started around here in spring 2020. This is 1 year from June. Oops, sorry about this. Yes, so this is from June 2019 to around now, June 2020. And so we see that people search, how the intensity of search for the word mask changes. So there was nobody interested, and around the end of January, there is one peak. And then there is a huge peak here around March, April. We can also see how people search for keyword Zoom. So Zoom is in red now. And we see that the change in user interest was much more abrupt. So people started looking for masks first, but then Zoom became much more abrupt, like sort of much faster, became much more relevant. So even though there is one COVID-19, we see that even this change is not synchronized here, which is, we presume, due to COVID-19. Then we see how people search for the word bank, and it goes up and down independently pretty much. Here, this is worldwide data, so there's this peak when Bank of America reported first quarter results. If you look at it in the US, this is much more prominent, this peak. But overall, we see that it sort of, the relevance remains, despite of COVID. There is no sort of change pattern. So if we presume that we make a model for user interests here, there is perhaps not so much that is changing here. And then finally, the word God. I was just curious to see, and then God is in green, and we see that it also does. The relevance of the word also doesn't change much. But while bank is very sort of volatile, God is always sort of constant, present in search. Except for if we go back past 5 years, this was 1 year before. So we see that there was a peak in search of God in around 2018, April 2018. So I was curious, I checked it. This is where God of War video game was released. So people were searching. Anyways, so the point is that changes are happening in our data, in our world, and we may want to reconsider our prediction models and decision support models in the context of changes that are happening. So what's there in what concept drift research has to offer, and what is not solved quite yet? So the world changes in many different ways. So here are a few patterns of how the world can change. So changes can be abrupt, something happens very suddenly. Changes can be incremental, drifts like here, gradual, bouncing back and forth. So here one can think if a user takes, let's say, a hobby, user interests might shift, but still going back to the past. Reoccurring concepts, if we're trying to predict sales of ice cream, for example, so we know that in summer sales will be higher, or maybe different patterns of sales will hold, but we don't know exactly when it happens. Every year it happens slightly differently and slightly different ways. So it's not exactly the same as periodic time series analysis. It's just sort of different state of which patterns hold in the predictive models. And then there may be outliers, so changes that happen very abruptly, very temporarily, and we need our predictive models to be robust as well, so not to react too fast and not to change things too quickly in reaction to outliers. So in classical machine learning, the main principle is collect. I mean, there is much more to it, but this is a very simplified view. Conceptually collect data which already has feedback, so the ground truth, train a model, validate, deploy, and then continue making predictions assuming that the world is not changing. Adaptive learning, which concept drift is about, makes predictive models and updates predictive models online automatically when new data arrives. And the critical part for that is receiving feedback. So if we are trying to predict the quality of chemical production, we need to know the true quality in order to update the models. If we are trying to predict credit risk of customers, we need to know the feedback which customers repaid or did not repay their credit. And there are basically two ways. There are many, many more, probably hundreds of ways nowadays, but the main two principles. So one principle is to have a procedure for making a model automatically from data and do periodic updates. This is often called a sliding window approach, like upstairs. So just let's say every week or every month, revisit and make a new model out of, or update the model out of the most recent, let's say, data of few months. And the other principle is to have a change detector in place or a trigger in place which monitors the quality or monitors the data and then signals when update is needed. And then when the signal comes, then the model is updated accordingly. And then there are lots of nuances and there is a lot of theory of how to update the model when change signal comes. So in practice, so far as I've seen, most of the approaches follow the first one. That is periodic updates. This is an interesting example, Yandex traffic jam prediction. Yandex is a Russian equivalent of Google. And I was a few years ago, maybe now 5 or 6 years ago, I was involved with them in a project predicting how long it takes to go from one place to the other in real time. And they were very open, and there's public information about their models. And the interesting part is that exactly what they do is, of course, they have their model contextualized for different times of year and different days, but they also update their model periodically. So they retrain it. So they have an automatic procedure for every piece of road segment. They receive the ground truth and they update the model on regular basis. I think on a weekly basis. That was the public information that was available. Yes, and then so as another dimension, so models can be periodically updated or with change detectors, and it can be a combination of models, and in practice it usually is. So multiple hypotheses are in place. Here is a quick illustration that you can make multiple models from different times of your data in the past. And then you can have dynamic rules to combine predictions of those models, or you can have rules to select which model needs to make prediction at what particular point in time. So ensembles in principle and in practice are very powerful ways. And the benefit here is that there is no need for complete retraining of the model. So you can store multiple hypotheses, for example, for seasons or winter, summer, and then just update a little bit and put them in operation. So the trade-off, yeah. So there are different strategies work in different types of changes. So as we can see here, if change is very sudden, usually it's better to detect change, drop the old historical information and make model as new as possible. If changes are happening gradually, then in these cases, periodic or windowing approaches are better. Windowing approach, like windowing or in general, periodic approaches are also more robust to outliers in general. So they continue their procedure no matter what, whereas if change detector is in place, it can be misled. Ensembles work well when there is a combination, something like that. I'm now simplifying the picture, but the principles are there. In reality, many different changes may take place, and combinations of that take place. So then strategies need to be, of course, tested and tuned accordingly, depending on what the expectations are. But basically, you can have a trade-off between very quicker action with a change detection, but the risk would be that then it quickly also goes out of tune or reacts to outliers, or you can have periodic, robust, large system with many models, many hypotheses in operation. It would perhaps be slower to react, but then it would be more robust in a way. I think I'll skip this one in the interest of time. Yeah, so now in the context, so what can we do if we want to understand the changing world that comes into circumstances that have never been seen before? So we can think about societal change, climate change, or even the state of society today in the context of COVID-19, where we don't know if we have ever seen a similar world like it is today, or like it has become. And it's very difficult to actually find equivalent data or equivalent world to extract our patterns from in order to make predictive models work in this situation. So basically the challenge is that the world is new and there is no feedback, not enough feedback yet to act or to make models more specifically, or to act in general. This situation, by and large, is also not so different from many contexts. For example, in credit analysis that I have experience with, sometimes models have to be made when economic situation has changed, like in the Baltics in the 90s, 2000s, when there is the system is completely or largely new, and there is no local data that would support that can be used for making predictive models. And especially if the economy is growing, there are not enough bankruptcy cases to base your model upon. So the solutions that have been made were proxies there. So looking for different ways and different proxies. If bankruptcies are not available, maybe delays of repayment can be used as proxies. So sort of creative thinking and approaching the problem from multiple perspectives, not resorting to just one model or one perspective or one way of making your target of prediction, or one way of making or extracting patterns. Similar in analysis of the fossil record, to analysis of evolution and life in the past. If we want to predict the patterns in order to reason about how the world works in general and how it may work in the future under climate change, there is no really ground truth of the past that can be used directly for making predictive models. If there was, then we wouldn't need models at the first place. So then again, the same principle applies, that if changes have happened, we need to make predictive models, we need to make predictions. but there is no ground truth data similar enough, then we have to find multiple different ways to go about it, and testing multiple models or multiple ways. So multiple ways of formulating targets is always good. This brings me to transfer learning, which is very well known in AI and machine learning. Transfer learning is one way to go about it. In image recognition, for instance, it's very popular. So if you don't have enough of labeled data for the exact task that you're trying to make a model for, you can use something that you would hope have similar internal structure, similar features, and then transfer those features for the relevant models. So there is an example of disease prediction as well. I'm a bit out of time, so I will not go much into detail there. But so the main principle is then to simplify your representation using some other similar data or similar circumstances, and then go from there. And this applies also to paleontology or credit scoring, or possibly traffic jams or anything that we would want to address in the new situation after the world has changed. Yeah, so what analyzing the past and analyzing and predicting the future can teach us, they all say that considering multiple scenarios and multiple hypotheses is important. This is not the same as having an ensemble. An ensemble is just having different models in operation. But this multiple hypotheses or multiple scenarios is broader. It's starts with the part when we collect our data. So if now we want to make models operate in the new or changed world, we would perhaps try to collect data and collect ground truth for extracting predictive patterns from different angles in the past. And yeah, from the historical data. So yeah, that was my short introduction to concept drift. There is a lot has been done in the last 20 years. If you want to start with something practical, concept drift detection, adaptive techniques, I can recommend start looking from this MOA machine learning experimental framework. It grew out of VECA, which is data, used to be data mining and still is a popular data mining benchmark software based on Java. Yeah, and so MOA is specifically for data streams, and it has a lot on concept drift. So adaptive learning strategies are there, and they have implemented pretty much most of the main approaches that exist today, and I have contributed a few years ago as well. So yeah, so that's one source to find more information, and that's all I had. My slides. Be well and stay healthy.
Thank you for the excellent talk. So we have time for at least one question. So let's see if we can see any hands here. So does anyone have a question or comment? We have also the chat as well here, so that you can write as well. So we don't seem to have any immediate questions from the audience. So okay, here we have something. So it's thank you.
Thank you. Thank you.
Thank you. So perhaps I will ask one question. So this concept drift is very interesting and useful, and it's part of this toolkit. So in a way we have this toolkit of different machine learning methods for building models, revising models, updating those and so on. And you mentioned also transfer learning as well. That's also one very important component of this toolkit. So, so now thinking about this current COVID situation, so that we would want to understand in a way the environment, like mobility patterns and these measures that are being taken, and then provide feedback for decision making. So in your view, so what would be important components of the toolkit? So I believe the drift, of course, is very, very important to understand here.
Yeah, so then the first question to ask would be whether do we want the toolkit to be in real time or not? So then the choice of techniques and components would depend on that. So if we want it to be real time, really, that would have to consider efficiency and scalability, and perhaps the important part would be reactivity, such that if we see any anomalies or anything happening, then alert is as soon as possible. So maybe, yeah. So those aspects. If we want it offline, sort of in retrospect over the last 2 months, so what measures should be taken? Should we reopen the airports? Should we put more buses, less buses, more trains, less trains? Sort of more strategic than operational decisions. Then different aspects of the technology would be important. So there then computational efficiency would be perhaps less important, and one can use also both sides of the data before and after the change, or sort of if you are trying to detect or track or monitor in real time, so you only have the past, but you don't have the future to make your decision. So if you can have it offline, then detection methods and alerts can be made relatively more accurate, because then you have both sides of the change that you can consider. So there would be, yeah, those trade-offs from detection from the concept perspective in a narrow sense.
Okay, no, thank you. So certainly there are these dimensions that we need to consider. So let's see, do we have any additional questions? So we don't seem to have now. So let's thank Indre again. So thank you for the talk. So I think we are now ready to wrap up. So thank you again for the talk and for the discussion. And I'll just share one slide. So I would like to thank the speakers again, and of course our audience for the questions and discussion, and for attending our webinar. And this was the last of the 4 COVID-related webinars we have organized this spring through FCAI and then HiDATA. And now we have the summer break coming up, and stay tuned for updates. So we have a great program planned for the fall. And here you can see the links. So you can see the link to FCAI and also to HiDATA. So please, if you're interested, go and have a look. And we will also make the recording available of this event through these links as well. But now, thank you again, and everyone have a really excellent and safe summer. Thank you, and bye-bye.